I want to take a look at improper integrals related to 1 over x to the p for different values of p here. We've done a couple of these. We've done a 1 over x squared. We've done a 1 over the square root of x, so that would be x to the half power. Um, anyway, we're going to use these as sort of simpler examples that we can tell convergence or non-convergence very quickly, and then use those to compare against other functions. So I want to take a look at some different things. First of all, I want to do p equals 1, because I don't think I've done that one yet. So that's just the integral of 1 over x dx. So I want to do both types of improper integrals. So first of all, let's just go from 1 to infinity, and then I'll do it up against the asymptote at 0. But let's just take a look at this one first. So we're looking at just 1 over x. We're integrating from 1 to infinity. So I'm looking at this area right there. The integral of 1 over x, the antiderivative, is the natural log of the absolute value of x. Evaluate between 1 and infinity. So I'm looking at the natural log of infinity minus the natural log of 1. Well, I know the natural log of 1, it's 0. But how about the natural log of infinity? Now, again, remember, this isn't really an infinity being plugged in. It's b, a big number. And the big number keeps getting bigger. And if you look at the natural log function, right, it has a vertical asymptote at 0, and then it heads off like this. But it's always headed uphill. And in fact, it will eventually get as high as infinity. It grows very slowly, but it does keep going up and up and up. And so this is an infinity minus 0, which is infinity, and this integral right here diverges. Right? Diverges because that's infinity. So that's going to play a crucial role in this process here. This integral of 1 over x actually diverges. Let's look at this area now. So let's do the integral from 0 to 1 of 1 over x dx. So we're looking at this integral right here, that area. Again, this doesn't look necessarily like there's an issue, but when you try it, you've got natural log of the absolute value of x evaluated between 0 and 1, which is the natural log of 1 minus the natural log of 0. Natural log function, 1 is 0, that's no problem, but the natural log of 0. Now, so I'm not actually plugging the 0 in, I'm plugging in values of x that are getting closer and closer and closer to 0, and looking at what the function values are doing. Well, the function values are headed towards minus infinity here. So this is infinity. This also diverges. Now, if you know anything about this function, you might realize that you would expect it to diverge, because this function is actually symmetric about the line y equals x. That this over here looks the same as that over there. So if this was infinite, then from here up should have been infinite, and then you add one more to that. That's still infinite. Right? So anyway, the integral of 1 over x diverges on both sides. It diverges as you head towards infinity. It also diverges as you bump up against that vertical asymptote. Okay. Now let's take a look at other values of p. And let's just do it in general now. This is 1 over x to the p dx, and let's do it from 1 to infinity here. So we're looking at something that looks like this. And I don't know if p is positive or negative or big or small or anything here. Just it's a number. But I do know that I can integrate it, because I'm going to write that as x to the negative p, integrated from 1 to infinity. And so that's going to be negative p plus 1 divided by negative p plus 1, and evaluate between 1 and infinity. So this would be, instead of saying negative p plus 1, I'm just going to say 1 minus p. This is x to the 1 minus p power divided by, sorry, I'm plugging the infinity in. Infinity to the 1 minus p power over 1 minus p minus 1 to the 1 minus p power divided by 1 minus p. The question is, what is infinity raised to this power? And it's going to turn out, and it does turn out, that it depends on p. Because if This equals two possibilities here. If p is bigger than 1, then 1 minus p is negative. So like p was equal to 2 or something like that. And 1 minus p would be negative. Then this thing looks like that infinity ends up in the denominator. So there's a 1 over 1 minus p in the denominator, but there's also an infinity to the p minus 1 power. I changed the sign as I put it down there, where p minus 1 is actually positive, and we're still subtracting this 1 over 1 minus p. So if p is bigger than 1, this thing right here, well, I'm going to put it like this, then this is a 0, right? Because there's an infinity in the denominator, and 1 divided by a really big number is really small. So this becomes a 0, and you just get, let's write it this way, as equal to 1 over p minus 1. I don't like that negative sign, so I'll distribute it into the bottom. Right. So if p is bigger than 1, then p minus 1 is positive, and you've got an answer of some positive value. On the other hand, though, up here, if p is less than 1, then 1 minus p is still a positive number, and this infinity is still in the numerator. This is a 1 minus p. There's a 1 minus p on the bottom here, but that infinity stays in the numerator, and hence an infinity raised to a power, a positive power, because 1 minus p would be positive because p is less than 1. Infinity raised to a positive power is going to be infinity. And so, so if p is greater than 1, then this is infinity, and we say it diverges. Right. Now we just showed ahead of time too that if it was p is equal to 1, then it diverges. So let's put an or equal to there. Okay. It really comes down to when you're integrating something like this, and you're going to be plugging an infinity in, does the infinity end up in the numerator or does it end up in the denominator? Dividing by infinity is a good thing. Dividing by big numbers gives you small answers, and hence finite answers. But multiplying by big numbers gives you really big answers, and so hence you get to infinity here. So it's just all a matter of when does the infinity end in the numerator, when does it end in the denominator. And that all depends on whether p is bigger than 1 or whether p is less than 1. Okay. Now, that was the integral from 1 to infinity. Let's now do it from 0 to 1 up against this asymptote and see what happens. Okay. So now we're going to look at the integral from 0 to 1 of 1 over x to the p dx. Again, we do it exactly the same way. I'm thinking of this as the integral of x to the negative p power, which I'm going to integrate. Oops, I got a page break here. I'm going to integrate to be, integrate it. So that's equal to this, which is equal to x to the minus p plus 1 divided by minus p plus 1. Evaluate between 0 and 1, which would be a 1. Again, I'm going to write this as 1 minus p over 1 minus p minus 0 to the 1 minus p over 1 minus p. Now, if you're not careful here, we might just say, oh, 0 to that power is always 0, right? Well, no. There's two things that could happen. If p is less than, well, let's do it in the same order we did before. If p is bigger than 1, then 1 minus p is negative. And this thing looks like you got a 1 over 1 minus p minus, well, if p is bigger than 1, then 1 minus p is negative, and this looks like 1 over 1 minus p 0 to the p minus 1, where with p bigger than 1, this is a positive power now, but it's in the denominator. So you got a 0 in the denominator. Well, 0 in the denominator is a tricky thing to do. Dividing by a small number gives you big answers. And this is not going to be good. Right? This is going to be divergent. In fact, let's just put there. If p is bigger than 1, this is infinity, and hence divergent. If p is less than 1, then I'm looking at this 1 minus p. If p is less than 1, 1 minus p is a positive number, so you got the 0 in the numerator, and that's a good thing. You got 1 over 1 minus p minus the 0's up here as a 1 minus p over 1 minus p. That's good. 1 minus p would be positive. 0 to a positive power is 0, and all I get is that. So if p is less than 1, then this is just equal to 1 over 1 minus p. We also saw that if p is equal to 1, it diverges, so let's put that right there. This is exactly the opposite of what happened before. That if you look at the graph, say, of y equals 1 over x is this nice symmetric thing. That here's 1, 1, and it's nice and symmetric. This is y equals 1 over x. If I look at y equals 1 over x squared, so let me grab a different color here. If I look at y equals 1 over x squared, it actually looks like this. And it sneaks down in underneath there. Y equals 1 over x squared. For big values of x, x squared is really big, and so 1 over it is really small. For small values of x, like say a half, if I take a half and square it, I get 1/4. But then I take the reciprocal, I get up to 4. So at a half, this is clear up at 4. So 1 over x squared is bigger than 1 over x over here, and it's less than 1 over x on this side. So this is getting close to that horizontal asymptote rather quickly, and we get a finite value. But on this side, it's taking its time bumping up against the horizontal asymptote, sorry, against the vertical asymptote, and that's infinite on that side. If you look at something smaller than 1, well, let's pick a new color here. How about green? If I look at something like y equals 1 over the square root of x, or y equals x to the half power, then that's actually exactly the opposite of this one, the opposite in the sense of reciprocal, and it sneaks in really close here, and it takes its time over there, right? If you plug in a 4, you're going to get 1 over 2, so by the time you're out to 4, this is only down at a half, right? 1 over x would be down at a 4th. So with these small values of p, then you get it kind of staying away from the horizontal. It does eventually approach that horizontal asymptote, but it does it more slowly, and you get infinite area, where on this side it hugs into the vertical asymptote, and you get finite area inside there. Okay. There you go, the integrals of 1 over x to the p.